So what kind of memory cells do you guys know? What kind of memory do you have? Be loud, guys. Primary, secondary. Okay. Okay, RAM, I know. What kind of RAMs have you heard? SRAM, DRAM. Okay, good. Well, now we have got noise in the classroom. What are DRAMs? What are they physically? Transistors. Well, transistors are used to access them, but most DRAMs are a capacitor. Right? It's essentially a capacitor which is holding the charge. But DRAMs are not typical capacitors. They are special purpose capacitors. Remember the way we make them. For making capacitors, you need a parallel plate. Right? If you saw the chip early morning, we had loads of parallel plates, but they were not big enough. So to make DRAMs, generally what we do, we drill a trench in the silicon substrate and then fill it with conducting material so that we get a big capacitor. If I get time, do remind me to show you some SEM images of DRAMs. Which means DRAM are actually, even though they are good memory, they take a very small area, it's just a capacitor. They cannot be built in every process. They have specialized process to make DRAMs. Okay, and actually below 14 nanometer process, DRAMs are not really being very successful. So we're using quite a lot of SRAM, yes, but DRAMs not. Now what's an SRAM cell? Have we come across an SRAM cell like this? So it's essentially two inverters back to back. So we have got the output of one inverter connected to the input of one inverter and the output of this connected to the input. So it's basically a inverter which keeps on regenerating its own output, and we have two access switches which are there to read or write. So that's for 1 bit. If I have 64 bit reads, I need 64 into 6 of these as well. You can immediately see that is not feasible on a chip. A deep network is very difficult to implement on a chip. A shallow network, yes. A small network, yes. The other problem which we have is we are actually camera designers. We thought we can have a neural network with the camera and then you can do anything in the real time. Right? Take a picture and tells you what the picture is. But my camera is already taking a large amount of area. We had already a large number of pixels. We have already got a large number of diodes. On top of that, I have to make these. It's very difficult to put them on a chip. So, yes, the industry is doing this quite a lot. There are a lot of people who are working on a digital deep neural network implementation on a chip, and there's a lot of work going on, don't get me wrong. I would like to argue that whatever you do in digital processes, the number of cells needed will still remain large, and hence so many cells will also consume a lot of power. Each of these, we haven't talked about power till now, each of these gates are consuming power. Even though in CMOS we say there is no static power, actually there is due to leakage. Dynamic power will always be there. Okay. So let's now go and see how do we make this neuron in analog technique, and is that actually any beneficial? Because I still have the same problem. I need to add, I need to multiply. So how do I multiply in analog? At the end of the day, I'm going to be very tired because I have to stand the whole day today. How do you multiply 2 digits in analog things? Yes, resistance is a good multiplier. It multiplies 2 things. That's not the only multiplier we have, do we? There are a lot of physical equations which try to multiply 2 quantities. Okay? So he talked about using the Ohm's law, which basically multiplies voltage with conductance. Okay. So in our configuration, we have no configuration, no shortage of such laws which multiply two numbers. We can have tons of multipliers. The other beauty is resistive multipliers don't need each bit multiplication. They are doing it all at one go. Right? But we don't like resistors. Few reasons. They're difficult to make, and we are making things small and small and small, and now you will come back and give me a 10 kilo ohm resistor. That will take a bit of area. They're even more difficult to make uniformly, because you're not only asking for one multiplier, you're asking for a million multipliers. And the worst of that, they carry current. Current flowing through resistor gives power, I square R. Right? So whatever I do, they will carry the, but they still do a very good job. Now how do we make, so we can possibly use resistors for multipliers. How do we make adders? How do we add to signal in analog? This has been taught even to first year students. Do you remember op-amp based addition? Like two resistances, one resistor, and that adds two signals, right? So remember, when we are doing this voltage based multiplication, we are getting a current output, right? Our output is current, so we need something to multiply, and that we have seen in undergraduate. So if we have tons of current, all of this pass through a op-amp based circuit, we will get adders. Okay. The question then comes is of memories. Not only I need a multiplier and adder, I also need something to store my data. Okay. So when the last time, artificial intelligence have had summers and winters. And by summers and winters, I mean sometimes it has been very popular, the cool thing to do, and then people stopped working on it completely. So it's not a new term which we are using. In 1960s, when computerization started for the first time, people thought, well, we have got an intelligent machine and AI is going to come and take all our jobs. 10 years later, it died. In 1980s, we had things called artificial neural network, ANNs, which were spiking neural networks. And once again, people thought, oh wow, cool, they can solve all these problems. And then they did this thing. 20 years ago, we started with this deep learning convolutional neural network bandwagon, right? Has it started dying already, or is it still going on? How many software engineers did Google and Meta fire in last 2 years? You guys don't read those news, right? You only read how many people got jobs, not how many people lost their jobs. So what happened about 5 years ago? See, industry works like sheeps. So everybody thought AI is the solution to everything. So a lot of engineers were hired. And now all of a sudden you realize either it consumes too much power, it does too much training, there's not enough data. It's good for centralized people like Meta or ChatGPT to come up with something, but not necessarily terribly good for all the simpler problems. So all of a sudden you're not going to have AI based people for doing this thing. The reason why I started talking about history of AI was last time when AI was cool, the way we were making memories were these flash memory drives or EEPROMs. All of you have used them, right? Do you know how they work? Has it been taught to you in your undergraduate? In your graduate studies? No? So the way these devices look like, they look like transistors, but rather than a single gate on top, they also have a floating gate in between. There's a second gate here. This gate is not connected to anything. So same source drain, There is a gate which is not connected, and then there is a top gate which is connected to something else. Okay? The idea is, by using tunneling operation, if I apply a high voltage here, some charge will tunnel through this dielectric and come on this thing. Okay? That charge staying there changes the threshold voltage of the transistor. If I want to remove it, I apply high charge to the body, and this charge comes to the tunnel through hot electron tunneling and then goes away. So that's how you program and discharge a flash gate. You're essentially, in the digital EEPROM devices which you have, it is essentially storing two values of threshold voltage. And if you remember your MOS transistor, you change the threshold voltage, you change the current output. Okay? So the threshold voltage can be used as something to store memory. Now you might ask, why only two values, 0 and 1? We can certainly store many different threshold voltages. Some of those who have done MOS design, what was the typical threshold voltage of your transistor? 0.6, 0.7 volt. So I don't have big headroom to change it dramatically. Right? So a lot of work actually has been reported in literature where people have used these memories to make neural network. But the interesting thing about these memories is the neural network would be this big on the chip. The control logic to control would be this massive right next to it. Because now you need to provide high voltages, right? And you're talking about a 3.3 volt technology, you're talking about 15 or 16 volt to apply. So you need charge pumps to produce that voltages. So brilliantly works, can be used, but cannot be reproduced, cannot be done with a large number of these things. This leaves us within a trouble. We can make multiplier, we can make adder. Our memory solution is not terribly good, particularly analog memory solutions. And this is where some hope lies in new type of memories which are coming up. A lot of it is in the research domain. We are also writing papers on that. Most of these new type of memories are not based on circuits, they're not transistor. Remember, all the memories which we talked till now, they are transistor based. Right? SRAM was transistor based, DRAM had a capacitor but still transistor based, Flash has got a floating gate, still transistor based. And this is where the problem lies. Virtually every foundry think their memory would be the one which will take the market. Remember, memory market is huge. And the whole reason okay, not whole, but I believe Samsung became such a big company because their memory business started flourishing. Okay. So number of memories which are there, and these are the words you will hear quite a lot. There is phase change memories, who change their phase, and phase could be resistance or optical condition based on applied heat. Okay. There is magnetic memory. In magnetic memory you have things wherein you are using a spin and orbit of magnetons or the torque in the tunnel. You have resistive memories whose resistance changes by doing something, by applying a voltage or by applying heat or giving energy. Somehow you give the energy to the system. You have ferroelectric memories which are kind of magnetic based. You have oxide replacement memories, you have conductive bridge RAM, and sometimes, like conductive bridge RAMs many times are similar to RE RAMs, but because of industrial pull and push, they are all being called different names. So every foundry has got their favorite, or they have got 2 or 3 of their favorite, hoping one of these will succeed in market. So right now in the stage wherein we don't know which one of these will succeed. The other issue is, remember, they are not transistor based, they are physics based, they are device physics based. So how they will scale? Transistors, we know, as we made the transistors smaller, the memory also started becoming smaller. How will these scale is an open question. So we are in that flux where a lot of neural network work is going on based on these new type of memories. We don't know which one will succeed, if any one of them will succeed. Okay. So with that warning that maybe none of them will click, I'll just introduce one of these to you because physically they are beautiful devices. Okay. And that's the devices called memristors. So ignore whatever is written on the circuit. So you knew things regarding voltage, current and charge. You know these 3 things. So the relationship between voltage and current, there is a fundamental material called a fundamental element of electronics engineering called the resistance, which relates between voltage and current. Okay, there is capacitance, which relates between voltage and charge, and of course between charge and current you have the time based relationship. We also have inductance, which basically relates between flux and current. So when we say d phi is L di, now flux was kind of one of the most ignored things when we learn. So we don't talk much about flux in our undergrads. We know what it is and then very quickly move to L di dt, don't we? So Leon Chua argued that if I put them all in a kind of a rectangular block, I have a relationship between this and this, I have a relationship between this and this, I have a relationship between this and this. So there has to be something which relates charge and flux as well. There has to be the fourth fundamental element. And he predicted it will be a memristor. It will act like a resistor, but it will also have a memory. It will remember its past states. So formulation wise, it's just d phi is equal to m dq. For a long period of time, Chua predicted its existence in 1970. It wasn't seen. It was one of those theory papers which was good to read, but no one has seen this. HP was able to show similar behavior in very thin stacks made of metal oxide. So if you had two conducting layer on top and you have metal oxide in between, they saw similar behavior. The beauty of these devices is you apply high voltage, their resistance changes, but the resistance remain that till you apply a very low voltage. Okay. Now we have been trying to make now the devices work fairly okay, they are still not stable. Nobody has been able to make 1,000,000 odd memristors. Remember, in order to make a neural networks, we'll at least need a 1,000,000 memristors to put the weights. We are also making them. We can barely make 16 by 16 arrays, small arrays of memristor. The other issue which has happened with memristor is, again, which material do we make of? So typically memristors are formed of 3 stacks. Again, I will bring some pictures tomorrow to you guys. So essentially the kind of memristors which we make, they have a top active layer, a metal layer, and a bottom layer. In between we put a dielectric. So otherwise it looks like a capacitor. Okay. Now if you take a very thin dielectric, it will have a high resistance. Right? It will have, and all capacitors have a resistance, it just have a fairly, and the layer thickness we are talking of is a few tenths of nanometer. Now what we have seen, what other people have seen before us, is that if your top layer is made of some metals, so in our case copper, silver, molybdenum, okay, and the bottom layer is neutral, all it does is provides a contact, it doesn't do anything. So we can make platinum or ito or any metal you want. So if you have a thin, say dielectric, something like silicon dioxide or amorphous silicon, and you have a thick layer here, you apply a certain voltage, what happens is these ions start moving in this dielectric. Okay, do I have a, oh, this is tied here, I can't remove it, but okay. So as ions start moving in, so you have copper on top and copper ions are slowly moving into the dielectric. If you keep on applying high voltage, at some point they go and touch the bottom electrode. Now as you can see, what has happened is I have formed a channel of copper ions. Copper ions channel will have low resistance. So something which had high resistance, by applying a voltage, it has now resulted in low. Even when I remove the voltage, these ions will not travel back on their own, because this is a solid structure, right? So ions will not travel back. Now I have got a low resistance state. The only way to remove the ions will be to apply a high voltage to the bottom layer and negative voltage to top layer, so that all the ions get attracted back. Okay? So this gives us two resistive states. Now by applying high voltage, I mean 1 or 2 volt we are talking about, right? So 1 or 2 volt of positive voltage forms the channel, 1 or 2 volt of negative voltage removes the channel. And I will show you some examples in one of our later lectures. Now the reason why this device is interesting, it is a resistance. For when I am not charging, when I am not applying high voltage of 1 or 2 volt, if I am applying 0.5 volt, it is a resistance. Okay? Which means it's a multiplier. Okay? The other thing is, I can change its resistance value. So when I am programming it, I can apply a high volt and shift its resistance. The people have also tried doing pulse and giving many resistance values rather than just a low resistance and a high resistance. You can have multiple resistance states in between, which means we can make something like these crossbar arrays, wherein, say that's my input signal V1 to so on. These can be multiplied with this memristor plus it's the same current, so current in series gets added. This can be multiplied, current in parallel gets multiplied with this resistor, this can be, and then we can feed this to a summing amplifier at the end. So and rather than designing each neuron, we just create these large arrays of memristor and then go and program each, because in a neural network the same input will be fed to many different neurons. So that way you have got, if that is the output of one neuron, this is to the second neuron. So conceptually they are very nice devices, and they appear to be potentially the future of neural network design. And if we can make them, if we can stabilize them, the problem with these devices is they are not stable. They still take programming. You still need a programming circuit to put high voltage or low voltage to make them work. There is massive variability in these. Every 2 memristor behaves very differently, and order to stabilize are still up in progress. So people like TSMC are trying to do it, but it's still very early stage. The problem of power consumption is still not very solved. They say these are consuming less power than our equivalent of digital logic, but the moment I use resistance, current will flow through resistance, right? And we will have power dissipation going on. So the only way to reduce that, because remember what we are doing, we are applying voltage across a resistance. So voltage is my input. So how do I reduce the power dissipation when I apply a voltage across a resistance? I can increase my voltage or I can increase my resistance. So V square by R. So if I can make, the problem which I have is the moment I make the bridge, I get a very small resistance. Okay. So the research direction which people are taking now is how do we increase the dynamic range of these resistors, how do we change the resistances so that we get lower power. So conclusion for the first 45-minute odd of the lecture is that the classical von Neumann computer which you have been using for so long makes very cheap and powerful machines. You all have a von Neumann machine with you, but they are not the ideal machines to implement neural network or artificial intelligence circuit. We can make a neural network out of digital circuitry which is available to us. Analog seems to do better job at this point of time, or at least looks to be doing better job at this point of time. It still has got all the issues of noise, variability, reproducibility, and those are still very high research topics for us to play with. But it is promising that if you're going down the direction of machine learning or neural network based systems, we might have to revisit the entire digital design the way we do it, or else power is going to be a big concern. Or else what might happen is we never go to, so you know how we went from large machine to personal machines. If we don't solve that problem, we will never have personal neural networks. So that is a research direction where a lot of work is going on right now. We don't have any solution yet. So we'll take a break now, and when we come back from the break, we have done 2 or 3 things today. We have looked at lumped parameter models in the morning. We have looked at neural networks. So why don't we do some exercise problems? So in the second half we will do some tutorials. Okay, I will come around and help you guys. We'll set the problems on the board, and then we'll do the tutorials. Because if I do another lecture, you guys will be dead. Right? There's only so much lecture we can hear in a day from a same person, and there's only so much lecturing I can do. I mean, I can talk another hours, but my brain is already dead an hour ago. And it's a day for fasting for me. It's Purnamashi. So I haven't ate anything, but so I think it's better we do some tutorials. Tomorrow morning I have been told the lab will be available, so we'll be now. Okay, before I let you go, so there are two things which we should have discussed about. One is neural network designed and trained, but there's another approach which is happening in research. Why do we need to constantly learn? So if a neural network has been trained in cloud or trained in data center, can't we just physically make that trained neural network with those parameters? Okay. If we have to do that, then we don't have to learn, we don't have to change the resistance, we just build finite resistances in the chip. Okay. How can we make resistances in the chip? So one is memristor. Say our process does not have memristor. What other ways we can make a resistor? We can make a long wire, that's a resistor. It's a small resistance. Or we can use a transistor. Remember, transistor operation goes up and then flat lines. The time it is going up, it looks like a resistor. It is a resistor. It's a voltage dependent resistor based on the gate voltage, and I can change its resistance slightly by applying different gate voltages. Okay, so we can use a transistor as a resistor. So one thing which we could try doing tomorrow, those who haven't done the image sensor, it will be a good idea if you guys go and do your pixels. Those who have done the schematic of the pixel, I will sit with you and we will do the layout, because layout is fun. And if you reach even that stage, then we'll try to make a perceptron, a simple neuron using purely transistor, no memristor, nothing else. Okay, good. Let's take a quick break now. Thing about Bihar. So I tried to fool it, thinking, okay, Arunachal Pradesh is a contested region between India and China. China claims it to be there, right? We don't think China should own it. It's part of India. So I thought, okay, you know what? When I asked in which country is Bihar, it gave me the boundaries of Bihar. So if I now ask in which country is Assam, it should give me the boundary of Assam to be Arunachal Pradesh. It seems as if like somebody had just gone to the head office and asked, what should I reply to this question? Let's try that question again. In which country is Assam? Okay, ChatGPT gives a decent explanation of McMahon line. Should we ask the same thing to DeepSeek? DeepSeek has figured out, don't try this guy. Let's ask anyway. What do you think would be the reply? Server is busy again. It will chicken out. discovered it's so fun to make fool of AI. And we had this, I was doing a Viva a few days ago, and we asked a question. Is it because we are based in India? Should we try me being based in Germany? Problem is, how can I blame even NIT network doesn't allow you to go to many web pages. I can't even do VPN to my own. There is this VPN banned here. Really? Why?